Ladies and gentlemen, we are back with a discussion on chapter 5. So in this chapter, we'll be discussing functions, how to write functions, essentially. And we're going to look into different perspectives on functions. So let's begin. So functions are a collection of statements that do something very specific, like reversing a string, uppercasing a string, computing square root of a given value, and so on. So we need to think of functions as black boxes, meaning you have inputs coming in, you got something happening inside the box, and then you got the output. So we are only concerned about what a function does as long as we are using a function, and we are worried about how a function will accomplish its task as long as we are designing and implementing a function. So we have actually used a lot of functions before, but let's take a look into the round function here that the book actually gives. So we are rounding the value 6.8275 to 2 decimal points. So since the third decimal point is a 7, the previous two will round to 83, so it would be 6.83. Okay. So we are calling the function round with inputs, and we're getting an output, so the price will be 6.83 floating point. So 6.8275 and 2 are arguments to the function. So the function, any given function actually, does something and returns something. Well, the book actually has a few things where you may actually get confused. So one of them is this statement that says functions may receive multiple arguments, but they only return one value. Well, this is a little bit confusing. It's true that there is actually a single value being returned, but that doesn't mean a single monolithic value. So if you could return a list, you could return a set, you could return a dictionary, tuple, or anything else actually that may hold multiple things, or that may be capable of holding multiple things in it. So if you were to return a list or a tuple, you would actually be returning multiple values essentially, or multiple monolithic values, or indivisible values. So it doesn't mean that you can just simply return 5 or 4 or just a string and that's it. No, you can return multiple values stuck in a single value. Okay, that's essentially what I'm trying to say. So we have seen an example of this, and I just dropped a note for you here to remind you that the div mod function returns 2 values. So let's switch to the notebook here. Let me just simply go here. Oops. So if we say div mod, let's say 17 divided by 3, we got 2 values. You see, this is actually a tuple. We haven't yet done tuples, but we'll see. So I can show you this simply by doing tuple assignment also. Or actually, let's just go step by step here. So here is the result. So we're not going to see it, but when you display result, we see 5 and a 2. Well, if you want to ask the type of the result, we will know that that's a tuple. Okay. Well, we can get both pieces out by doing what's called tuple assignment. So I'm going to get the quotient, and I'm going to get the remainder all in one go. So when I display the quotient, I get 5, and when I display the remainder, I get 2. You see? So even though it's returning a tuple type, it's a single value. It's a single value, or it's a single data type. But actually, I'm able to hide 2 things inside. So this is a good way to show how you can return multiple values. It's not limited to 2. It could be it could be any number of them. but usually we're not going to return too many values. So we have another function called random function, which we discussed in the previous chapter. So we call the random function, and it returns a random value. So here is how the round function works. We get two arguments. We got the black box that does the rounding, and we get the return value or the result. Now, big thing here that I added for you that says do not confuse printing with returning. So we're going to talk about this more, but we need to be explicitly returning a value to get a value back outside when we call a function. So we are the implementation of the round function is actually explicitly returning a value so that we could store it in this value called price. So printing just sends things to the screen. That's all it does. Doesn't do anything else, doesn't return a value. So you should not be using print to return things from functions. So do not confuse the two. And we're going to talk about this more when I switch to my notebook. So when we are using functions as black boxes, meaning we are just simply using them, we're just worried about what arguments we should send to the function and what the function will do for us. So we don't really need to know how the function really does its work, but we have to worry about that when we are writing functions. So we're only concerned about what the function does. So when we design our own functions, we're also going to make them look like black boxes to others, because people are going to be interested in using the functions. They're not going to be interested in, unless they have a special interest in it, in how the function actually has been implemented and how it works. Like I suggested to you, self-check exercises you should do on your own. I may go through some of these, but you should do these things on your own and just check back, because the answers are in the back of the chapter. So it's a really good way of testing your knowledge about how much you learned, and if you are unable to answer these questions correctly, then then you have to work harder. That's what it means. So how do we implement and test functions? So suppose we have the cubes, like a box like the one here, and we want to compute its volume. Well, we need to decide on a name for this function so that it's meaningful. It conveys the meaning of what the function will do, and we need to decide about again the arguments and what we're going to call those. So to compute the volume of a cube, we only need the length of a single side, because all sides are equal. So we need to start with a depth, and then we give the name of the function. This is something that depends on what how we want to do it. So it depends on us basically. Def is a keyword, so we do def, the name of the function, open parentheses, a list of arguments. Here there's only one, so we only have one variable name. So the way we're going to compute the volume is taking the cube of the side length, and we're going to also have to return this value called volume that we computed. So here's our function. We compute the volume, store it locally, and then return that value. We could just simply do return side length taken to the power 3, but we want to do this so that we can actually inspect what value we have out of this computation. Then we test it, which means after we define it, we call it a couple of times at different values and compute these values by hand and see what we get out of the function. So we got 2 and 10, so 2 raised to the power 3 would have to give you back 8, and 10 to the power 3 would have to be 1000. So if you get that, that means you have done your work right. So this is a simple function, but this is how it goes. So I again colored this return statement for you here, so that you know that return statement is something that you would have to put in to return a value. Actually, before I go on, let me switch to my notes again. So here are a few things. So we have used some of the math functions, and you get a bunch of them here. We have the sine function, and we can get help on I'm gonna comment this out for now, because if I press on it, it's gonna get me a long list of things. And here's the sine call. Of course, everything in the math functions work with radians, not with degrees. But we should know that 90 degrees is pi over 2 radians, and therefore 180 degrees would be 1 pi radian, and 360 would have been 2 pi radians. So the type of the variable, or the unit of the variable, is also really critical. So when we are passing something in, we need to know exactly what unit and what type of data is expected. So here I gave you the example of sine. I meant 93 degrees, but I got back not one but something else, because what I'm really passing in is 90 radians, but I want to pass in 90 degrees. So even if I do math, but you see, since I'm doing it properly the second time around, math pi over 2 is actually the radian representation of 90 degrees. Therefore, I get back what I expect, which is 1. Okay. Well, if I want to convert this value 3.14 represented in a string to an integer value, I'm going to get back a value error, because I'm trying to actually convert a floating point value, put in a string into an integer value, and that's not going to work. But a floating point conversion would work just fine. Even if I have a bunch of spaces, I can convert this value to integer, because what it contains is an integer value. I have multiple values, it's not going to work. And I have something funny, again, 5x, it's not going to work. Okay. So we can get help on all these things. So I'm going to cut this up, because this was there actually right above. So I just pick one of the values from the math library here. So it's the ceiling function. It just tells you how to use it. So we can just use it to get the ceiling, which means the closest value to 3.14 that's higher than 3 is 4. And when you take the floor, you essentially get the integer part. And here you get the integer part that's higher than the value itself, or the closest to the value. So 3.14, the closest next full value or integral value is 4, so that's why you get that. So you have a bunch of functions in the math library, as you can tell. So we get the factorial, floor, all kinds of things. Before I go back to the book, I alluded to it a little while ago that working with units is critical. You always have to carry along the units of what you do. So if we want to convert degrees to radians or radians to degrees, we have to make sure that we are multiplying with the right value and we're dividing with the right value. So let's take a look at these formulas. So to convert degrees to radians, you have to multiply degrees with 2 pi radians divided by 360 degrees, because 2 pi radians is actually equivalent to 360 degrees. And if you want to go from radians to degrees, we need to multiply the radians by 180 divided by pi. But what we are really doing is that we have d in the unit degrees multiplied by 2 pi in the unit radians divided by degrees again, and you will easily tell that degrees in d and degrees in 360 will cancel out, and we will be getting radians on the left hand side. And the same thing here, radians would cancel out, we would get degrees. So this is how we should work. So we can do an example here that we have 270 degrees. I want to convert it to radians, so I have to divide degrees by 360 to get the ratio of how many degrees I have, and multiply that with 2 math pi, or 2 times pi. So we expect to get 1.5 radians because 180 degrees is a full radian. So 270 would be half more actually. So since it's not very intuitive to know what 4.7 radians really means in degrees, we want to we can just double check on it by just multiplying. This is supposed to be 1.5 times pi actually, and that's in radians. So if I multiply 1.5 with math pi, I should get the same exact value, and you can tell that I'm getting the same exact value. We're going to come back to this in just a second, and when I go back to the book. So now we want to talk about this return statement again. So I meant to actually talk to you guys about that, but I think I have that discussion later on. Let me just see if I can grab it here. I have it here, but okay, I think I'll just do an example and then later I will just run through this. So let's just do this cube volume again. So let's go site length. I'm going to change the way it's typed. So, oh, sorry, this is code. Raised to the power 3. And then initially, actually, let's just do it this way. Cube volume print. So I'm going to be printing this volume out. Okay. So now, so since I have this defined, I can call cube volume print. Let's just put 2 again. Well, looks like we are getting 8 back, right? So if we are getting something, a value back, or if it looks like it got printed, so it looks like it got returned, we can double check on this by just capturing the value. So I can say volume 2 here, cube volume again 2, right? This time I'm not supposed to see anything, but anyway, I see a value again. Well, when I do V2, I get nothing. Well, what does really V2, what is it? There's a value, obviously, because unless it was undefined, I would be getting, if it was undefined, I would be getting an error, but I didn't get an error. But I know what this thing really is actually the value none, because implicitly this function returned the return value of a print statement, which is none. But it didn't really return the volume, it just printed it out. So it's not really returning, it's just printing to the screen like it did here. Okay. So we need to write this function properly the way it was done in the book. So I'm going to call this the return version. We don't need in parentheses, so I'm just going to get rid of that. So let's just do the same thing. So cube volume return. Again, let's just do 3 this time, so I get 27. But if I do v3 cube volume return 3, this time I'm not going to see anything, obviously, because the value got returned. It did not get printed automatically. But this time, v3 would also have a value. So unless I return, there is no way I can capture this return value. So I must return. I cannot print if I mean to return. Of course, we can have a print statement here. Nobody says we cannot print anything. So So I can actually just do volume of the value that I'm going to pass in is equal to the value that I compute. So I get in the side length, and volume is my answer to this question. So I can just, you see, volume gets printed, but I also have V3 being 27. Okay. So later on I can just comment this out and then just have it not print anything out. But still my program or my function here is returning a value. So that's very critical for you to understand. Do not confuse the two. So you have to be careful that if you are using a function, actually if you are calling a function, that it's already defined. Well, here we are calling cube volume, but cube volume is defined after this statement, so therefore this is going to fail because you are going from top to bottom as the Python interpreter and you see this call. Well, then you try to make the call, but there is no definition because the definition is coming later on. So this will fail. So we can actually hide this test portion in another function. Let's just call it main. So we have the result captured here, and we just print it out. And then we have the second definition. Well, even if we are calling cube volume from here, we are not really calling anything right now because we are just defining it as part of a function. So this is just a definition. This cube volume can come from anywhere, but we are not really executing the function. We're just simply defining it. So we also defined a function here. Here is the call. So I should point out to you that finally we call main, which calls cube volume. Okay. So this is how this thing is going to work like. Finally, this is the call. These are definitions. So again, so don't confuse function definitions with function calls. This call will be made once main is called. Print is going to get called if main is called. But here we are defining main, not calling it. We are calling it only here. So from here, this function would be executed, and then the value would be returned to the result, and the result would get printed out in this sentence. So again, these are described in more detail. So here is the actual function that you can take a look at. So all these things, as you know, you can get from the code that's available under textbooks in my Dropbox link, and you can just run these things on your own, change things around, try your own things, and see how it goes. And if you run into problems, then you can try to fix those problems and then learn how to look better. But you have to be running these things and tinkering with this code. This is quite simple right now, but it's going to get more complicated. So you should get used to editing, looking at this code as you're studying. So we got more questions here. So it's asking what's the value of cube volume 3. You would just be running it, but we just did it anyway. What about calling cube volume 2? So let's do this in here. The proper version that will return a value is, well, actually, let's just do it with both. So let's just put a little border around. So let's call cube volume print and call cube volume print inside with 2, or let's just do it with 3. Okay. Okay, let's go. Uh-oh, I got a 27 out of something here, and then I have something is wrong here, right? Because I was explaining, under normal circumstances, this first call inside should return a value, then that value should be an argument to this function again, then we should finally get another value. but we are getting something that says none type and int. You are trying to take the power, and it's just not working out. Well, remember, this function doesn't return anything, meaning it actually returns none. So we need to try the return version to see, because return actually returns a value, and here we get two print statements, but it's basically 27 raised to the power 3. But if we just do this too, we can double check on it, because first we're going to get 2 to the power 3, we're going to get 8, and then 8 is going to be raised to the power 3. So 8 times 8 times 8. So 8 times 8 is 64. 64 times 8 will be 512. So finally we're going to get back the value 512. Okay. You could actually make cube return, a third call, a call inside a call inside a call. So that's why you have to make sure that you return, not print, to mean return. You can always print, but print will never return. Right. There is a programming tip here about including comments. And the book says comments are for human readers first and foremost, for you, for me, the person who's writing the code, and not for compilers. Compilers cannot understand the comments. You need to explain what your function does, what arguments it takes, what outputs it generates in detail. And that means we need to be really good communicators. As engineers, you cannot just simply write programs and forget about everything else, because we're not going to remember what we did and how we did something if we don't document what we do. So comments. I just added this thing for you. And actually, I meant to also write documentation. Now, there is a mention about the Doxygen program, which is going to be processing these kinds of things written before the function in this format, and it would generate a HTML document. But the book doesn't suggest the docstring idea, but I strongly recommend that you actually write docstrings instead of this kind of documentation, because this is natural to Python, and docstrings are part of the program, so you can actually print them inside the interpreter, but you cannot print this side. This is just purely comment. Docstrings are part of the program, so you can actually get them. So it's just like this. You can also format these as well, so there's nothing that stops you from going from this kind of documentation into a nice HTML generated output. But use docstrings. So the book says we don't use this style, but many Python programmers do. And in this case, please follow the many Python programmers and use docstrings and not this kind of commenting. So again, this is a critical deal here. We need to distinguish between how and what. So the function comment does not document the implementation, meaning how the function does what it does, but rather its design or what the function will do for somebody. So this is what a black box actually is. We describe the what rather than the how. How is something that we worried about when we were writing something like cube volume, because we're implementing, so we need to worry about how to do this. But once this is done, we're just using, and so on. So we only worry about what will we have to supply as input, and what would we be getting, what we would be getting as output or as return value from those functions. So the distinguishing between how and what is also critical. So I just put a little note here for you. So we can make pies if we put in cherries as input. Then we make a cherry pie. If we put in apples, we make an apple pie. So it's both are pies. It's the same function, but depending on the argument, you get two different results. So we need to also be passing parameters to customize how functions will actually do their work. So cube volume accepted a single site length argument. So we created a local variable to keep track of the result, and then we return that result. So the parameter site length is actually an argument to the function, and it will be created when the function is called. Then this value will be initialized to the result of the operation, and then we would be returning it, the value. But where do we return from? Where the function was called, wherever that happens to be. So some more examples for you to work on. All these I need you to do and then check, because these are rather simple. I'm not going to go through them myself. There's a suggestion by the book that says that when you take in parameters from an argument list, don't change this thing. Like since I'm using it here, and then I'm just reassigning it to a different value, to the same variable sense. Instead of this thing, the book suggested create another variable and store it in there, which is something that I agree with. So, and then we should keep in mind that all variables that we create and initialize within a function, unless declared global, will be created and will only be known within the body of the function. So their values will not be reflected outside unless we get some compound values, but we're going to look into that later on. But like you have singular values like this, and you create this thing called price. This price will never be known outside. There may be another price outside, but it will never be known outside. It will only be known within the function past this line. So it will not be known before, it will be known after. So at this line, you know what price is, but it will be removed and deleted after we return from the function. So return values are everything. So we could write the cube function simply skipping the local variable creation. We could just say return site length raised to the power 3. And we could also check if the site length is less than 0, we return 0, and then we just do this regular computation. So if the function happens to be called with a negative value, then we just go into this statement. So we have an if statement that checks if the site length is less than 0. Otherwise, we would be putting in this part of the code, so we would be doing the regular computation. But we need to make sure that we return. See, so we are returning here. So if we have something like this, the site length is larger or equal to 0, then we return. Otherwise, we don't do anything. What happens if we pass in a 0 value? Well, if we don't have an explicit return statement, we will return none by default. So here it is. Site length is less than 0. We need to return 0. If the site length is not less than 0, then we compute the volume and return the volume. But we need to, either way, we need to make sure that we return a value. If we don't do this part, and we happen to put in a negative value, and we don't have this actual return, we're going to be returning none. We always return something. It's just that we return none when we don't have any explicit return statement. So here we go. So it says that if we don't do that, none will be returned. So there's always something returned. So what we should do is actually put in an explicit return 0. So some people, I can say I'm among them, don't like returning from within if statements and things like that. Instead, we just store the values we want to return in a variable, with the same name, and then at the end we put the return at the end of the function. So this is a choice. but it's a fine choice as well. It may be clearer this way in the sense that we know that there is only a single point of return here instead of multiple return values here. So if we change the body of the cube volume function to this, would it be any different actually? Would it work different? Well, we can tell that we are also including 0 here. So if the side length is less than or equal to 0, we're going to be returning 0. Otherwise, even though we don't have an else, we're going to be going to the statement and we're going to be returning the actual volume. So it should work just fine. Well, instead of writing these kinds of things like if digit is 1, return 1, if digit is 2, return 2, to actually convert numeric values to English words that mean the same numbers, we can just put them on a single line instead of just taking extra lines to write them. So this is just a fine way of writing. So we can just do it like this. So let's take a look at this example and then see how we can implement a function. The problem statement says that we are helping an archaeologist who research Egyptian pyramids. You have taken on the task of writing a function that determines the volume of a pyramid given its height and base length. So first of all, we need to describe what this function will do. And we can just say compute the volume of a pyramid whose base is a square. And then we need to determine the inputs. To be able to do this, we need to think of everything that will be varying. Well, height and side would be those two things in this case. What would be the types of the parameters? In this case, both would be floating point, the height and the base length. What would we be returning? We would be returning the volume, again, as a floating point value. So we decided we want to call it the function pyramid volume. Maybe we want to take in the height and base length. You could actually reverse the order of these things, but as long as you specify which is which, it's fine. So as long as it's clear that is. And then we can write pseudocode for this. So volume is 1/3 times height times the base area, and base area means base length times base length of base length square. So here we go, pyramid volume given height and base length. First we have to compute the base area. That's the square of base length because the base will be a square. Then we just multiply the base area with the height and divide it by 3. And we can test this function and print things out and see whether we have done everything correctly. So you should run this at home. You may want to include it, copy and paste it into your notebook, or you can do if I can show you, I did this before, but let me just do it again. So I can run Python again, but I forget the, let's see here. I need to go to textbooks, and then like this. Okay, that's the chapter. So let's just run this. There you see. So we can run it like this. So you can run them by putting Python and the full path, and then you put in an exclamation, and that will just be running an external command, and it will just be running it. So, but the thing is, you should see the source code, so you should definitely look at it in the book. And then you can go in and change some of these values and try your own version of the program. So here's another example: generating random passwords. Many websites use passwords, and we're going to be doing these things randomly. So first of all, description of the function. We'll be writing a program, not a function. So we'll write a password generating function and call it from this program's main function. So it will generate a password with a given number of characters. We could include multiple digits, special characters, but we're just going to include one of each. So determine the function's inputs. There's only one parameter, the length of the password, how long you want it. Determine the types of parameter variables and return value. At this point, we have enough information. So parameter will be length, which will be an integer value, and we'll be returning a string. So when we say make password, given a length, we will be getting length number of characters with random characters, and so it would be so we will be getting back a string with length number of randomly chosen characters. So let's just write pseudocode for this. So we can say that we'll make an empty string called password, randomly generate length minus 2 letters, and append them to the password. Randomly generate a digit and insert it at the random location, and generate a symbol and insert it at random location. So we ended up completing length number of characters. So here's a function to actually get a random character from a list of characters, and then we'll have an inserted random in a string, and the string to insert. So we're going to have a for loop. So we're going to have letters A through Z. There's a better way of getting this, but anyway. So we're going to be calling our function called random character. We're going to pick a character out of this randomly, and we're just going to add on top of the existing password. So we're going to start with an empty password, and it's going to be we're going to have password plus this new character, and then there will be the new password. So we're going to keep doing this thing length minus 2 times. Again, we're not using I, so we could just be using underscore here, which would have been much nicer because we are not really using I for anything. And then we will be getting a random digit, and then inserting that at a random location in the password and getting the new password. Then we will be picking a random character out of one of these symbols, again inserting our password in a random location in the existing password string, getting the final password, and we'll be returning this password. So far we don't have, we're just imagining we can write something that would do the work of random character picking, and then we have something called inserting at a random location in the string. Well, testing would just require us to call make password with a number of characters we would like the length of the password to be, so we then print the result. And we can get some, here are some random values that the book actually tells us. So first, so we have divided the problem actually into 2 parts, or essentially in terms of the functions, we have 2. Random character picking and insertion at a random location in a string. So we repeat the same process of running through the description and the design of a function. So we can do the random character picking first. So what do we have as input? We have a string, and then we pick one of the characters in return. So we have the length of this. So the pseudocode would be something like this. The length of the input string would be n. So we measure the length of the string, and we pick a random integer between 0 and n minus 1 so that we cover the whole string. And then we return a substring of characters of length 1 that starts at r. So this would be the random location of the character we're going to pick, and we just grab that particular character out of the string that we have input, and so we return that. So that's the pseudocode. So random characters picking would be a random character taking in a list of characters, or actually a string of characters. So we have the length of the characters stored in n. Then we generate a random integer value from the random module between 0 and n minus 1, and we just return that character at that location. We can test this by just picking 10 random characters, and you can put this in a main function called main, and then have this work. So here are the characters we picked, 10 of them. Since we put n equals 0, we are just printing everything on the same line. So the second is the insertion at a random location. Well, again, like we always said, can you do this thing by hand? You are given a random location in a string, and you're asked to insert a new character in that location, and you're supposed to return the string. So we have a string, another string, a substring. This will actually be a single character. You don't have to care about that. And we're going to have to insert it at the random location. Nobody tells us what location. We're just going to have to pick the location randomly. So we have a bunch of choices. It could be inserting something at the very beginning, and the first location, second location, and so on, or also at the end. So 0 minus, from 0 until, so the indices could be 0 until n minus 1. Actually, in this case, the range would be not 0 until n minus 1, but it would be 0 until n, because we can actually insert something past the last character. Since we're inserting something new, inserting something at position 0 would mean before the string or before the existing password. And storing something at location n would mean storing after all the characters of the string of the password. So we take the length of the string, we generate a random integer between 0 and n, inclusive, that is, and we get all the characters in string from 0 to r. And then we insert what we need to insert, and then we add the remainder of the string. So here it is. We take the length, we generate a random integer from 0 to n, we store it in r, then we start. We start with an empty string, we run through, so we run r times from 0 to r minus 1. So we just pick every single character until r minus 1, and then we insert what we need to insert in between, and then we start from r, go until n, and then add the remaining part of the string, thereby creating the new password with the second string inserted at a random location. This random location will come from random integer function. We don't know exactly what location, but it will be limited to this range, which is inclusive 0 until n. So I'll let you guys take a look at the testing. So we have a bunch of these things created. So, and here is the function. We can run that again by just copying this. So this just one. If I just run it again, it should give me another one. Try run it again. It should give me another. Um, so we can tell that actually. Let me just run this once again. Okay. So we can tell the integer value got put in the second position, and the symbol got put in a different position. Now, the book actually confuses us by saying functions without return values. This means functions that do not explicitly call the return statement. But actually, all functions return a value. So functions that do not explicitly return a value return none by default. That's what actually happens, and as you can tell from the things that we have done already so far today for this chapter. So I'll not go through this because it's a simple box printing function. Again, you're doing print, 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 and there's nothing else. There's no explicit return. This particular function will return the return value of the last statement it executes, which is this print call. Since print returns none, this function will implicitly return none, but it will nevertheless return none. So our big goal here is actually to turn a set of statements that solve a small problem into a function, so we can keep using it, such as all the string functions we've been using and all kinds of other functions like the math functions that the entire world is using, which whoever is programming in Python ends up using those. So we want to package our algorithms in functions so they become reusable, which means we define them once and call them many times from anywhere in our programs. So here's an example. We are entering a value between a low value and a high value, and as long as that value is less than low and higher than another one that we specified, we say that your value is out of range, so just input another value so that it's between low and high. So you guys can give this a try. So we can tell that while loop here will be checking this condition, and if this condition is true, it will stop. And if it's I'm sorry, if as long as the condition is true, it's going to keep going. And if the condition fails, which means the value is between low and high, then it would just be printing the value that happens to be within this range. So if we enter something outside the range, so we enter 25, but we want something between 0 and 23. 25 would be out of range, so 20 would be in range. -1 would be out of range, and so on. So by all means, read these sections. They are very informative. You will be learning a lot of nice things about the computing world. So I'm not going to go through them myself, especially in my video like lectures. But please read these. It's they will be very informative. You will be learning a lot of nice things out of these panels here. Now, problem solving is our big thing in engineering. And we also need to learn how to do stepwise refinement. We cannot just simply attack the whole problem, especially when the problem is a really big one that requires lots of detailed steps, and just try to do it all at once. So we need to go from top level to bottom level. So this is a good example, and the example is about brewing coffee. So can you ask somebody for coffee? Yes. If so, then you ask that somebody to bring it. So the problem is getting coffee. So if you can ask somebody to do it for you, fine. If not, then you need to make coffee yourself. Well, how can we make coffee? Well, we may want to do it with instant coffee. Well, if we so we ask the question and you have to make a decision whether we have instant coffee. If we have instant coffee, we make instant coffee. Well, what does it take to make instant coffee? Well, we need to boil water, and then we need to mix in and mix water with instant coffee. That's how we get instant coffee. But the thing is, mixing is just a very easy task. We don't have to divide it up into smaller tasks. But boiling water is more complicated. So how can we do that? Well, do we have a microwave? If we have a microwave, we can fill a cup with water, put the cup in the microwave, turn on the heat for 3 minutes, and then we have hot water. If we don't have a microwave, we can fill the kettle with water, and then turn on the kettle and wait until it boils the water, so we can get boiled water. Or we can just use a regular saucepan, put water in it, and then boil the water on the burner. See, so we are actually refining an abstract step into an actual set of steps that we would have to go through. So this is how we can handle instant coffee making. If we don't have instant coffee, then we have to brew coffee. So we need to add water to coffee maker, add filter to coffee maker, and grind coffee beans, add coffee beans to filter, and then turn coffee maker on, and then wait for it to drip down, and so on. Well, grinding coffee beans would have to be refined again uh, because we would have to add the coffee beans to the grinder and then turn the grinder on for 60 seconds to be able to do the grinding of the coffee. So this is the refinement. So is this part. So you see, making coffee has this refinement. This whole thing actually is making coffee, and making instant coffee has this refinement, which one of which is the boiling water part, which is refined into this whole thing. And brewing coffee as grinding coffee beans part, which is refined into this whole thing. So this is how we should actually work. So here is a problem about converting numbers into words that mean the same thing. So you take in, so this is the pseudocode. So you take the part that needs to be converted. So that's the name of the number, and then if the part is more than 100, then you say name of the hundreds in part plus 100, so it's like 300, 400, and then you remove the hundreds from the part. Then if the part is more than 20, then you have to add the tens part to the name, remove the tens part from the number. Then if the part is larger or equal to 10, then we need to handle the teenage numbers, and then you set the part to 0. And then if the part is larger than 0, you still have some single digits, and you just name the single digits. So here is the refinement for handling only the digits part. So digit name is here. So if the digit is 1, return 1. If it's 2, return 2, and so on and so forth. So we can see this is digit name. This is one refinement. Then handling the teenage numbers is another refinement. So we go from 10 until 19. So these are all teenage values. Then we have the tens. So if we are between 20 and 90, we have 20 until 90. And then we go back to the function that's going to get called. That's going to drive this whole program and do the actual work. So we start with the name, which is an empty string. We're going to keep tagging along or tagging onto the strings that we're going to need to convert this value into a word number, actually. So if the part is larger than equal to 100, so we're working within the range of hundreds and below. So if you have so if we have the value 274, it would be represented as 274 in words. So we divide the part, which is the integer value, by 100, again integer divide, and then we turn this into a digit name, and then add 100 onto the name. And then we do the modulus, which means we take the remainder out of the division by 100. So you would only be getting the digit part. The 100 part we'll be throwing away. And then we just keep doing like this, but if we're doing in the 20s, we have to do the modulus by 10. And then here, we don't have just a single value name like 100. We have different tens names, 20, 30, 40, 50, and so on until 90. So we need to handle that part with the remaining part value. And then we'll be taking the part value down in the tens. So we need to then take care of team name part. And then finally we go into the single digits. And then we just turn that into a digit name. So we have digit name, team name, tens name, then we have int name. So we got 4 functions, but this int name function calls these other 3 functions to handle its work. I'm sorry, then we have digit name, so we have 1, 2, 3, 4 functions that it calls, plus this one 5, and then we have the main driver that calls the int name. So one challenge here is that you want to think about without looking at the answers, that is, how can you extend this function so that you can handle values up to 9,999? You need to think about this and see if you can answer the remaining questions. We need to, strive to keep our functions short. So if you need to write, pages and pages of code for a single function, it means you need to refine or divide the work into separate functions and then reorganize your work, just like the int name function. We could have written the whole thing with all these details in there. It would have been much more difficult. But we have 1, 2, 3, I'm sorry, 3 calls actually, sorry, digit name is repeated here, that we are calling from within this function, and this function ended up being short, but we are actually taking advantage of 3 other functions that are themselves, a few lines long. So we should strive to, shorten our functions by carrying work in, that's specific into other functions. So then we can trace functions, again, taking in the value and then running through, on paper, and then running them essentially on paper, like I've been telling you guys, and see whether it would be working or not working, and see where you are actually falling short. Sometimes you just want to write the function, write the argument list, and just simply return something that may be meaningful or not meaningful, so that we can know exactly how we are going to be organizing our functions. These are called stubs. So stub is just a function with the proper name, list of arguments, and just something with a single basic return value that may be meaningful or not meaningful, but just something that that it returns. So we can still call these functions, no problem, but we will be getting mumbly, something. We're not going to get the actual correct result, but at least that we know that they are there and we can call them properly. It's just that their bodies are not yet ready. That's what it means. So here's another example for computing or calculating the course grade. Please go through this thing yourself. because I have many more things to cover as far as this chapter is concerned. Another thing that I want to alert you to is using a debugger. Debugger is a special program that allows you to or helps you find errors in your programs, and these are especially logical errors. There are many Python debuggers that you can use, but you need to get used to them. I think the Jupyter Lab notebooks don't have, well, they have a debugger extension, but it's a more difficult thing to get working. But you can use one of these ready-made programming environments like Spider, PyDev, or PyCharm that come with a debugger. But I can show you how I do this usually. So, for example, I'm going to be using this test Newton. So here is my program. I can run through all these things in such a way that would help me, debug errors. But of course, this program, as far as I remember, is a working program. But I can do something like this. Newton.py. Well, this program is running. One way is to go in and import the IPython debugger. So if I'm calling Newton square root method, I can just make everything stop. Well, just let's say here. So IPyDB, I will call set trace, and I'll just rerun this. Oops, I never set it. Supposed to be IPDB. So we can tell from here that we got stopped at line 47, which means we have not yet done 47. We switch to it, so I'm just going to do this always on top. So line 47 is right here. So I have done steps equals 0, so I can actually check steps, so you can tell that steps has been set to 0. But I've done something else unintentional. I just actually ran step command, so I just went ahead and went in into this thing. So I'm just doing it one step at a time, but I'm just going to do get help so you can see what you can do. There are several things like setting a breakpoint, continuing running, and things of the sort. So I'm just going to run through this real quickly, but I'm just going to say let's see here, break at can I do line 57 maybe? So now I set a breakpoint, which means execution will automatically stop. So if I continue bit C, execution will stop at 57, and then I can inspect again what the value of Y is. If I continue, I'm going to come back to 57 because this is an infinite while loop. It'll keep going until I have a certain difference being less than epsilon satisfied. So I can just keep on calling this because I was computing the square root of, let's see what value that was. So I can check for A. So A is 9, so I'm trying to compute the square root of A, so I'm going to have to keep going some more. Probably at some point, you see, I just reached a value that's very close. So finally, I just executed the break, so I just got out of the function. So we have a few things that we can do here. There's a stepping into a function, but I don't have a function that I would be calling here, so I cannot show you that I think at this point. Um, but I should come back to this uh, debugging issue with more detail for you guys. So here's a debugging practice for you, but we'll have to come back to this because I'm doing things in Jupyter Lab. You guys know that, but you can just run like I just did, and then uh, uh, do debugging that way. But there are multiple ways we can do debugging. But it's a critical issue. And so you need to learn your tools. One of those tools is the debugger tool. Well, scope is about what a particular name is known at a given point in a program. So the book says something very similar here. It says the scope of variable is a part of a program in which one can access it or one can see it. Well, the scope of a function's parameter is the entire body of the function, but not outside the function. So site length is known only within the body of this function. There may be another site length someplace else, but this site length is this site length. And once you leave the function, that site length name will no longer be known. So a variable that we define within a function is called a local variable because it's local to the body or the text of the function. So when a local variable is defined, the variable will be available from that point on until the end of the function. It was defined. So we have sum. So sum would be accessible in this part. We have I would be known within the for loop and actually past that. When we define square, it would be defined past this point. So next time you come along, you know what square is. So then sum is known here, but actually this is where we're reading it the first time we go into the for loop, but it was already initialized, so it would have a known value. If you take out this, sum would have no definition, so we need to initialize it. So that's another critical point. When we need initializations, we better make sure that we have initialized values. So a loop variable like I is also a local variable, so it would be extending beyond the for loop within which it's actually meant to be used. So I would also be known because it's past the line it's defined in, but we have not yet out of the function, so from print I we can still know it. So site length is known here. But we're not passing anything in. So this is a different version of this cube volume function. We have a site length cubed again, but the thing is site length is not going to come in from anywhere, like it's not going to be known here. So this site length is known only within the body of the function, not outside. So when we call it, this is in a box, you can think of it that way. You run in, you call cube volume, you go to cube volume. Where will site length come from? This is in a different box, this is in a different box. So you will get an error actually.